Okay, great. I appreciate everybody's participation in that section. I'd like to move on to our pretty much final section of this session, and I hope we have enough time for it. As I'd mentioned in our initial deliberations with the architecture study team, we did have some explicit questions that we'd like to get some feedback on. And as I mentioned in the introduction, we'd like your feedback here now, but we'll also accept it written and electronically, and I'll show you how to do that in the last slide. But the first question is, how would you prioritize enhancing the system performance characteristics in terms of spectral coverage, spatial resolution, revisit time, swath width, et cetera, to satisfy or advance your particular applications? And I think we've talked a little bit about this already. I'll allow the panel to comment first, and then I'll go to the audience if anyone.
I think I did just comment on that, right?
Okay.
I think we all have already commented on that, and as far as the cryosphere, I think that is the revisit time is the number one priority that we would like to see for reasons that I mentioned earlier, and that other members of this panel have mentioned, but in particular, snowmelt processes. 16 days is just not enough.
Yeah. Any further comments?
Yeah, we heard the messages from everybody about, to some extent, spatial resolution, revisit time, and so forth. Is it worth commenting on spectral coverage and swath width or any other key parameter? Increased, less, either way.
Let me try to answer that a little bit, because there have been discussions about some of these things within the Landsat science team to try to give a little bit of perspective. There haven't been any real strong proposals for individual new spectral bands to add. Okay, there's been some discussion of a red edge band and that sort of thing, but that the legacy set plus the Cirrus band now, which is really proving to be critical, is a pretty good set of bands. I think everyone would prefer hyperspectral data if that was a choice, right? I mean, if we had the opportunity to do that, that would obviously be a welcome thing. And the other issue that you were asking about specifically was swath width, is that right? You know, swath widths out to, 15-degree view angles and that sort of thing, I think would be welcome as a solution to getting higher frequency of observations. If that's kind of what you're looking at.
So there is a pretty strong view angle dependence on the surface temperature. You're seeing different proportions of hot soil versus cool vegetation over partially vegetated scenes. Out to about 15, 20 degrees, most models can accommodate that. Beyond that, when you get into the most very oblique view angles, a lot of models develop some biases strongly off nadir. But we would also welcome a wider swath for water resource.
Talking degrees from nadir, plus or minus? Yeah.
Right. Right.
Do we have any questions from anyone on a remote dial-in? We have another question from someone here in the audience.
It's actually part of the same question, and I would like the panel to address, what about applications with shallow water penetration? It seems like there could be quite a bit of improvement there, and there's a million questions to be answered there.
Again, in the preliminary results within the Landsat science team, we have a couple of people who are working on shallow water and coastal water related issues, and the big increases in signal to noise ratio and the resulting radiometric resolution pay off tremendously in that domain. That's the incremental improvement from Landsat, prior Landsats to Landsat 8 is going to be substantial. And so that's an issue going forward.
Okay, let's move on to the next question. And this kind of bears on Randy's 3 C's that he brought up. regarding the importance of instrument data calibration. And I guess the question that I'd like to pose is, to what extent could radiometric performance in terms of signal to noise or radiometric uncertainty be relaxed? And I'll start with the panel on that.
You know, where do I think we stand with this? You know, we've been through this huge jump. You know, Landsat 7 was a jump compared to Landsat 5, right, which was welcomed and valuable. But the jump now to Landsat 8 is dramatic. And in fact, the performance of Landsat 8 far exceeds the specs. And so in one sense, what we're dealing with for the first time is really top quality data. And can we back off from that? And it's been hard to test that because we've never had this quality data before. And so at the moment, there are a number of studies underway to try to understand, as you back off from where the performance we are in Landsat 8 towards, for example, what the spec was for Landsat 8, all the way back down to more what we got from Landsat 7, we're going to start to be able to answer those questions, but we're really still in the middle of that. And we're trying to do them in the context of the timetables that you guys have to work with. But I don't have good answers to that at this point in time.
Any comments from anyone else here in the auditorium?
I couldn't agree with you more, Kurt, that it's extraordinary. ALI was a major step forward, and then this was picked up by OLI, and something that was done marvelously. In fact, my understanding from speaking with Kurt Tomei is that it's so good and so stable that there have been requests to actually almost back off of it, largely because of the apparent striping in the imagery, because it's so consistent. But the real question there is backing off of it. If you're going to use this, and as I think I heard this when I came in from a few of you, that it could form basically the Cadillac for the Pintos, being the other nation's national guides. It's such a good standard that it could be used to intercalibrate against some of the other missions. So for Landsat 8 to continue to concentrate on this, I think is an excellent idea, with the ability to extend your observation space to incorporate observations from less capable satellites.
I believe we have another question over here.
I guess one thing I'll just mention is to reiterate something Curtis said. I think this question is well worth asking in the context of cost and cost benefit. But I personally also want to reiterate that the point that Curtis made is that you want to keep moving in a generally positive trajectory. You know, we have a 40-year legacy of data, but we've got a lot more than that. We've got a 40-year legacy of fantastic engineering in support of Earth science, and I would honestly not wish to see us lose that.
Quick point, signal to noise ratio for the snow and ice is obviously something that we don't want to be degraded, because we've had such a major advance with Landsat 8, and we certainly don't want to go back.
I think certainly the 12-bit quantization, once with 12, never back to 8, and I would certainly agree with that. And I think that's a lot of what I'm hearing said. I'm more concerned about the extra money that is being spent to try to get things back to lab spectra. The concept that you would know enough about the in situ atmosphere that you could have the calibration accuracy so that you could drive it back to what you might see at a lab spectra. I think that's wasted money. I don't think you ever know enough about the atmosphere. Maybe you could fly your UAVs and get a lot of in situ data, but without that, is it really worth the extra money? We do a lot of work in change analysis, and we do zero. We'll do TOA, top of atmosphere for sure, but to try to make guesses about the atmosphere, in my opinion, my experience, you end up messing up the data more than improving it. And I think the calibration from what we have been using, by the way, I'm MDA, John Dykstra with MDA. I was interested for the users. There's no industry on the panel, but there are a lot of us in industry that do use the data, and that type of calibration has not been useful.
I'd just like to mention there are a couple issues involved in your question, because one is the absolute calibration on the sensor, but the other is how you get from there to surface reflectance. And Curtis mentioned earlier this issue about cirrus and its impact, and it maybe just be the tip of the iceberg in terms of atmospheric effects that we may or may not fully understand and be able to model. But those are two different things, honestly. The sensor calibration itself and then how we get to surface reflectance, which is also important, they're related, but they aren't exactly the same thing. And I understand what you're saying. So I just want to make sure that we understand that the instrument calibration and the means by which we get to surface reflectance aren't really directly related in some ways. One of the things you could ask is, if you did want to get to surface reflectance, how would you do it? In other words, would there be additional bands, concurrent observations with other sensors? There are other things to ask that are associated with your question, but I just wanted to clarify that.
I think there's also been, some productive discussion about what is it you need. Do you need calibrated instruments, or do you need calibrated data? And for many of the applications, calibrated data is what you're after, and there are implications for cost in that decision as well. But while you may not be using the absolute calibration much in your work, there are many examples of people who are. So it is.
In terms of instrument calibration, you don't even need to involve the atmosphere any longer, because Landsat 8 points at the moon, and there's no atmosphere there, and that's the primary source for doing the calibration along with the solar calibration. So if you nab the instrument down, that will help you improve your atmospheric models if you have vicarious calibration on the ground, if the game is to get after surface reflectance. But in this day and age, we're interested in climate change, and the top of the atmosphere radiance is what we're after. And if we measure that accurately, we can then determine subtle changes that are needed at a high accuracy to look and to verify what direction climate change is going in and global warming. Those are sorely needed. We know what the incoming solar radiation is with high accuracy. We certainly don't know what the spectrally distributed outgoing radiation is, and that's essential to being able to understand the mechanisms and really what's happening to the climate.
Are there any comments or questions from anyone off-site? Okay, I'd like to move on to the next question and actually dissect this one a little bit further than what is on the chart. How important is the simultaneity of spectral coverage in the visible near-infrared with the shortwave infrared and with the Wiener SWIR and the thermal infrared simultaneity? In other words, what would happen if we disaggregated those wavelength regions onto separate platforms? And how would that impact your applications?
And I can understand there's some practical reasons for going that way in terms of modularity and perhaps having multiple thermal instruments flying and fewer shortwave instruments. So I can see some pros to that. I can also see a lot of cons. You certainly wouldn't want separation in time of more than a day from a phenological standpoint. You have significant changes in surface conditions, land surface temperature conditions on a day-to-day basis. So, if they're separated by minutes, that's less of an issue. I get more concerned about shadowing effects, changing topographic shadowing, and that's influence on the shortwave bands and the thermal bands, which can change very, very quickly. Cloud conditions, cloud shadows. are an issue. And then the ability to really accurately co-register the thermal and the shortwave bands. And then finally, delivering these data as a package, all stacked up, is such a benefit to end users. And somehow we'd have to get to that level of data delivery, because the end users are not going to go through this geo-registration process. They just want the data delivered in one package. So I can see saving some money, but adding an immense amount of complication to the whole processing system and introducing lots of potential errors into your retrievals.
One dimension of this that doesn't so much have to do with the thermal data, but it has to do with the optical data, is the ability to detect clouds. And as soon as you separate them by even a matter of minutes, you're going to lose some of your ability to screen clouds out of the images that, even if you aren't going to use the thermal data, which she obviously needs, but not everyone does. And so the ability to screen clouds, to lose that thermal dimension would hurt.
And as I mentioned earlier, following on from that, you need the cirrus band if you're looking at the thermal data, because if you really are interested in measuring the temperature, not just relative temperature changes, but absolute temperatures, then you need to see if there are cirrus clouds in the atmosphere that are throwing off that measurement of temperature.
Any comments from the audience? We do have one in the back. If you'd wait for the microphone. And
Hi, yes, I'm Chris Crawford. I'm a postdoc here in the cryosphere branch. One thing I'd like to also point out, as working with some of the new data, is to applaud Landsat 8 for its quality assurance band that characterizes the accuracy of at the pixel level, which I think is an excellent improvement. And then also with the cirrus band is the cloud ice properties can confuse the surface node signal. So I think that work there to kind of improve the ability to discriminate that is also notable.
okay, I'd kind of like to follow up a little bit, refine the question further. Are we collecting the right SWIR bands today? Do we need both?
There are certainly examples of applications that use both. And I thought it was very interesting to see in the chart that you put up that this SWIR band showed up sort of second, right behind the infrared band as the most important. And I think if there's been a trend over the history of the Landsat program, it's for increased importance in the SWIR bands. That if you look at the applications and the developments and the things that have come along and the new things that have come, that's been the portion of the spectrum, I think, that's sort of changed most in its relative importance through time as we've done this. And so are they the right SWIR bands? That's a tougher question, but there aren't huge choices in terms of where to move them. And two, there's certainly good arguments for two.
I think you'll find that we may be coming back to dig further on this to find out which of the two are the priorities to have. Dorothy?
If you move those bands, then you lose the continuity with the earlier Landsats, and so that is definitely a problem. And one of the things that we've said over and over is that we really think that the continuity with the earlier Landsats is very important.
And just to point out, there are operational programs that use the SWIR bands. For example, the normalized burn ratio that's routinely calculated by the Remote Sensing Application Center of the Forest Service to take a look at fire extent and severity, uses both the near infrared and the TM, ETM, and OLI band 7.
Do we have any comments from anyone off-site? If not, let's move along. Do the thermal data need to be collected in the sun-synchronous orbit as they are today? And this kind of gets back to the fact that if one approach may be to disaggregate the thermal data from the Wiener and SWIR. Martha?
So there's a lot of steps going from an instantaneous land surface temperature acquisition to daily evapotranspiration estimates, weekly, monthly evapotranspiration estimates, and it all hinges on having some kind of metric that is conserved over the course of the day that you can establish at that Landsat overpass time. And commonly it's the ratio of actual to potential ET that is used to upscale to daily or between Landsat overpasses. If you have that land surface temperature acquired at kind of random times during the day on different overpasses, you're going to add an additional degree of freedom or degree of noise in that interpolation process. I think we're not well served by mixing up that overpass time. We get kind of a more consistent capture of the land surface conditions if that time is stabilized. You also have potentially more clouds developing in the afternoon than you might have in the early morning times. Our algorithm in particular uses geostationary satellite temperature rise data during the morning to kind of establish a coarse scale normalization pattern at the continental scale, and we use the Landsat data to spatially disaggregate that. For us, it's very beneficial to have that overpass time shortly before noon about exactly where it is. And consistent from acquisition to acquisition.
Any comments from anyone in the audience? Anybody off-site? Okay, we'll move along. The last question on this chart, how important is the 10 a.m. mean local crossing time? And this is whether we fly all spectral bands in aggregate or disaggregated. I mean, that's what we've been flying today, but there are other systems that have departed from that and planned systems that have departed from that. How would that impact?
I think from a cloud standpoint, the conventional wisdom has been that the early morning acquisitions, not very early, but shortly before local noon, are less likely to run into cloud cover issues over the majority of the land surface. So I think it's beneficial from clear sky acquisition standpoint.
I'm not really sure how to answer. There will be issues, particularly in areas of higher topography, associated with changing illumination angles that will undermine the continuity dimension to the whole thing. But, I'd have to think about just how bad that would be. We haven't really had that to test, right?
Mm-hmm.
That's part of the problem.
Yeah, I don't have an answer for this, but I do want to point out that from the continuity perspective, the earliest Landsats were at 9:30. So that's, and that Terra and Aqua, the work we've done to establish what we're doing with EO1, indicated that there was, even though the perception was there that the clouds were were least damaged at 10 or shortly thereafter, they've discovered that even in the afternoon that it's seasonal and there's just no clear indication of when the best cover is. But I'm afraid the continuity argument is, we sure don't want to go back to 9:30, I'm pretty sure.
Any comments from anyone off-site?